Hi everybody, this is Mr. Folly again for part 2. I figured out my problem. All I had to do was hit escape. Oh, how clever. So we were talking about, first of all, cations and anions, and I want to tell you that cations are positive. So cats have paws, right? And a little mouth with little fangs. And that's how you remember that cats are positive. And anions don't. Okay? So I explained why cations get smaller, but I didn't explain why anions get bigger. So if I have my nucleus right here, and I'll just put positive charge right here, and I've got an electron here, an electron here, an electron here, an electron here. If I add an electron, ooh, I should change colors. Ooh, look at me and my new tablet. Ooh. If I put a new electron here, wouldn't it push this one away and push this one away? So what was originally my, what was originally my size of this, when I push it away, becomes my size of bigger. Right? So the added electron adds extra repulsion. Extra repulsion pushes electrons out. Okay? Ionization energy. So the energy to remove one electron from the valence shell of a gaseous atom. Fluorine is a Mac Daddy. Francium is a big loser. Okay? So ionization energy is the energy it takes to remove one. So if francium is a very big loser, it will lose electrons easily. So fluorine is small and attractive because it has so many protons per throw. So it takes more energy to remove an electron. Note how I redefine the track. Note second and third, etc. ionization energies are possible. So you can keep pulling them off and keep pulling them off. Okay? Ding, ding, ding. Ah! I should tell you why. Fluorine, or francium is a big loser because it is big. Francium is big, lots of energy with lots of energy levels, and few protons for its row. So it doesn't take much energy to remove an electron. Like, you guys live in a wonderful place. People aren't saying, man, I got to get out of this dump called LaGrange, Western Springs, whatever it is, Burr Ridge. It's a good place. You're not dying to get out of it. Now, if you grew up in the middle of nowhere, you might think different. Just to show you how this is periodic. Starts low and goes high. Boom. Starts low, goes high. Boom. Starts low, goes high. Boom. If we have another one, starts low, goes high. Boom. Whoops. So that's what a graph of ionization energy looks like. Reactivity. Get back here. Get back here. Metals react by losing electrons. Francium is big and unattractive, so it is the best reacting metal because it is the best loser. Nonmetals react by gaining electrons. Fluorine is small and attractive, so it is the best reacting nonmetal because it is the best gaining. Oh, why does it keep going on? So trends in reactivity are both. Okay, so this goes up and this way for nonmetals. Ooh, I'm going to change colors. You watch me change colors. Woo, wait. Maybe not. And then this one is down and to the left for metals. Okay? You have to make sure you know where your metals and nonmetals are. This is a review for prep. Excel can go to the next slide. So you need to know ionization energy, electron affinity, electronegativity, ionic radius. All have definitions. You must memorize. Actually, we got rid of electron affinity, so there we go. Ionization energy, and we don't have to worry about the exceptions either. Gee whiz. Size, refraction, and shielding. Explain it all. Shielding applies to vertical trends. Fluorine is the Mac Daddy. Francium is a big loser. Now it's so. Goodbye, prep. Toodles. Ionization energies can be used to predict the family. Leading to full, stable, small, and attractive noble gas state requires a huge change in energy. Okay, so notice here, this is about 500. This is about 4,500. Oh, sorry, that's about 4,000. I'm just looking at the change. This change is about 4. Ah, what'd you do? Get back there. So I'm telling I've got a super sensitive guy here. No. Come on. Okay. So this is about 500. This is about 4,000 more. Right? This is about 2,000 more. This is about 3,000 more. This is about 5,000 more. This is about 3,000 more. This is 4,000. This is about 4,000 more. This is about 5,000 more. This is about 4,000 more. Oh, get back. This is about 4,000 more. And this is about 120,000 more. Do you see it becomes an exponential change, like a power of 10 in these two spots? Okay? So going from first to second and going from 10, so actually it's, so leaving the first and leaving the 10th are the huge ones. Okay? So if leaving the first is huge, what that means, here's my periodic table. Leaving the first one means you're leaving the noble gas state. Okay? So that first one is 496, so this is my first ionization energy, and it lands me on my noble gas. I'm right here, which means I'd be small and stable. My second one is a huge jump, so that tells me that it came from the first energy level. Okay? If my huge one was the third one, then what would happen is the first one would be small, the second one would be small and land on noble gas, the third one would be huge. So whenever you leave the noble gas state, leaving the full, stable, small, and attractive noble gas state requires a huge change in energy. So my huge change in energy was right here. So this is when I left noble gas, and it was right here, and this is where I left noble gas. So that's it. So I will say toodly-oodly-oodly-oodly, and yay for my new computer. I'll figure out how to make it work better next time. Bye.